research laboratories of British Telecom, a new technology takes shape. One that will help lead the country into the next generation of communication systems. Systems that will be based on optical glass fiber. From a glass rod or preform, only a few centimeters in length, may be drawn 3 or 4 kilometers of fiber. Such fibers, perhaps only 125 microns in diameter, are manufactured with incredible precision. Using infrared radiation generated by lasers or light-emitting diodes, information can be transmitted along the fibers with little loss of signal strength. During the next few years, optical fiber will play a central role in helping to modernize the country's telecommunications network. The system works because the light that enters the glass fiber is internally reflected, so it travels along without escaping. Transmission losses are quite small, no more than 2 or 3 decibels per kilometer, so its use for telephone systems is highly satisfactory. Some experimental routes have been operating in the United Kingdom for several years. A considerable expansion of operational routes is now in progress, with some completed and many more being either installed or planned. From 1984, no more new coaxial cable routes will be ordered. Each fiber consists of a glass core surrounded by a cladding made of glass with a lower refractive index. These are protected by primary and secondary coatings, usually made of a thermoplastic material. Several fibers will be contained in a single cable, the exact number depending on its use. The carrying capacity of optical fibers depends on the rate at which the information is transmitted. The systems now coming into use are 8 megabits per second, equivalent to 120 circuits, 34 megabits per second, equivalent to 480 circuits, and 140 megabits per second, equivalent to 1,920 circuits. And all this is possible using one pair of fibers, each finer than a human hair. To carry the same number of circuits as an optical fiber cable, conventional cables are much thicker. So compared to the drums of coaxial or multi-pair cable, fiber cable drums are far smaller and much lighter. Operationally, this brings many advantages. Transport and storage costs are reduced, and handling and installation are also proving a lot easier. The new cables also occupy less duct space. This can be particularly important in parts of the country where installing new ducts would be difficult and expensive. In cities, too, where ducts are already crowded, fiber cables are showing themselves to advantage. There are also technical benefits due to the fact that the fibers are carrying light. They're not subject to interference, there's no crosstalk, and they're electrically isolated. Fiber cable is installed using established procedures and can be accomplished regardless of weather conditions. The light weight of the cable reduces the sheer physical effort involved. Routes installed so far have helped British Telecom personnel become familiar with the techniques required. The outer wrappings and layers are stripped from the cable to reveal the central strength member. To the end of this is now fitted a special pulling eye. There's also a mechanical fuse. This is designed to break before the stress on the cable reaches a level which could harm the optical fibers. Heat shrinkable bands are used to seal the cable end. Care must also be taken during installation not to bend the cable too sharply, as the fibers could then be damaged. The cable is pulled through a lubricator box before it enters the duct. At present, the cable is generally installed in lengths of up to 2 kilometers, depending on the route. For underground sections, to reduce cabling tensions, the cable can be figure-of-eighted and fleeted at an intermediate point, so shorter lengths are actually pulled each time. The lengths may be connected to others laid underground, or as here, may link up to an aerial section. For most aerial installations, an elevating platform is used, although ladders can be employed if necessary. The cable is erected using established techniques. A lashing machine is used to secure the cable to a supporting catenary wire. With the lasher positioned and loaded with a reel of wire, the cable can be clipped in position below it. Once this has been done, installation is very easy. On early routes, up to 2 1-kilometre lengths have been erected in one day. On one of the routes in Wales, the cable had to be laid along the bed of a lake. This was at Tylwyth Llyn, and the length of cable underwater was about 2 kilometres. In this instance, the cable was fitted with plastic bottles to provide buoyancy while it was pulled along the surface to the landfall at the far end. The floats were then removed, allowing the cable to sink to the bed of the lake. For this application, the cable used had an additional armoured layer to protect it against damage. In fact, there have been few problems of installation on any of the routes tackled so far, whether these have been subaqueous, aerial or underground. The experience gained by the British Telecom staff involved has been of great value in planning the extended use of optical fibre systems. On this route, once a length of cable had been laid, it was tested to ensure that the fibres had not been damaged during installation. This was done using portable equipment developed for the purpose. The operator checked the integrity of each fibre in the cable and recorded the transmission loss for that length. Another critical factor is the making of the joints between the lengths of fibre. For a perfect joint, the two ends are buttered together precisely and the flow of light is unaffected. A gap between the ends, however, will cause a loss of signal. There can also be linear displacement. This and angular misalignment will cause problems. When compared with a good joint, it's clear that these faults, alone or together, will prevent the signals from entering the next fibre correctly. The initial system adopted by one contractor for their fibre joints used a 3-rod assembly. The prepared ends were laid in a jig on top of 2 rods and carefully aligned. Index matching fluid was applied. The top rod was placed in position and, after a thorough test, clamped. The completed joint was then mounted on a base plate. Injection welding was used to finally seal the sleeves to the collar. The hot plastic cools and sets, providing a pressure-tight seal. British Telecom have developed a different jointing system. The fibres must have the primary coating removed. The ends are then cut square and to length. They are positioned in the jig and aligned by the operator while he looks through the microscope. They are fused by an electric arc, a technique which gives an excellent joint. The welded joint is placed in a small support channel and covered in epoxy resin. This protects the exposed fibre. The joint is now positioned on the base plate. The joint is closed using heat-shrinkable bands to seal the sleeves and collars. The yellow tape indicates that the cable is fragile, in this case because it contains optical fibre. Both British Telecom and the proprietary system joints have proved satisfactory in operation, and the techniques have been quickly learnt by those involved. So optical fibre systems are proving to have many benefits. The ease of installation, the greater carrying capacity, and the other technical advantages all confirm that optical fibre cable will play an increasingly important role in telecommunications in the future. One other significant benefit is that because of the low signal loss along the cable, repeating units are needed much less frequently. In many places, the need for buried repeaters will probably disappear, as existing British Telecom buildings can be used instead. This will also simplify installation and may eliminate the need for power feeding along the cable. New units have also been designed to interface with the fibre cables at the exchanges. Over the next few years, as more digital exchanges are introduced and the digital transmission of speech and data by cable expands, optical fibres will be an essential component of these communication systems. Television signals, too, whether picked up from satellite broadcasts or relayed by local transmitters, may well travel the final link to the home along optical fibres. This will be particularly useful when videotex systems are more widely used. The practical experience gained from operating the current systems will help British Telecom and their suppliers maintain their leading positions in this exciting technology.